Greetings, friends. We are somewhat back here on Wednesday of week 15. So this is class number 1 for us this week. So I haven't posted the PLC for this week, but I will do that. It's a traffic light, so just a bit of self-assessment, red, yellow, green, and off you go. Put in some critical thinking about the places where you were feeling really confident and also the places where you were not feeling really confident. I'll start off some of the filling in of the tasks or the skills or whatever you might think for you to traffic light. And I suggest you put in a few more so that you can really get a good handle on how it works for you. Just a reminder, homework 7 is not for turning in. But its problems will be fodder for the final, at least as far as we can get in the class. So some of the stuff on there may be things that we will end up not covering in the course of today and tomorrow. If that's the case, I will assess by the end of class tomorrow as far as we've gotten. And you'll know, like, if we haven't done stuff. Just be aware that if we haven't done stuff, those aren't going to be things that you'll be responsible for, but make sure it really is stuff that we haven't done and that you weren't absent that day or you didn't remember we did stuff like this. So final's going to be Wednesday. That's a week from today. I guess today's the 13th. It's Wednesday the 13th. I'm not sure if that means something. But anyway, it's next week. The mechanism will be as usual. It will be open during the day, and you'll have the final exam time to do whatever it is that you do. Cabrillo does offer 3-hour finals, which was new for me when I got here. So that's the paradigm we're following, and so we go. That's what we do. I wanted to talk more about the Bohr atom, put in a couple of things about how to get from one place to another mentally, and I wanted to extend a little bit of stuff so that we could use some of the quantum mechanical thinking to talk about more, maybe the Schrodinger equation, and maybe a little bit more modern applications of things, but also devices. Maybe I was hoping we would be able to get to talk about lasers and also radioactivity, but we'll see how both of those go. It's going to be fairly light on either one of those if we even get to them. So let's continue with the Bohr atom because I think that's what we were doing. And I was telling you that it's a model of hydrogen, which is the simplest possible element, and it works really well to describe what goes on in hydrogen, but it does not work well if there are any other things going on. So, for example, what happens when you put hydrogen in a magnetic field, what happens when you have an electric field, what happens when you have multiple hydrogen molecule, that type of thing. It tends not to work. It's really good for one specific situation, and that means it's a great first step in terms of a model because it addressed some of the things that needed to be addressed in order to make the model, but ultimately it can't be a good model going forward if it can't be generalized, and that's what we want here in physics, is to be able to use one model that takes care of a lot of different things. Okay? So the Bohr atom was a hydrogen setup, and it introduced us to, just to give you a list here, some of the things that it introduced us to, excuse me, is that there's a gap between energy states, or I should say there are gaps between energy states. And this is, I would say, one of the most fundamental ways of thinking and / quantities that come out of quantum mechanics, is that there's a gap. And the question is, how do we explain the gap? Another thing that comes out of it is that the wave particle pictures have been kind of blurred. And we now have matter that acting like waves. Well, this is not really a Bohr atom thing. This is really a de Broglie wavelength thing, but I'll show you how it applies. Excuse me. There's unfortunately going to be quite a bit of that, so sorry about that. Matter acting like waves actually is an explanation for why there's a gap between energy states, and I'll show you why. Imagine that you have this is an orbit, right? So there's your nucleus in the middle. I don't know, whatever orbit this is, doesn't matter. Let's say it's a 4. So I'm going to, what am I going to do here? Okay, I'm going to do this. The electron acts like a standing wave because at this orbit, the wavelength of the electron constructively interferes with itself. If I then make this orbit too small, just a bit smaller, then this wave won't fit around it, and it ends up effectively destroying itself with many repeated circumference, I don't know, whatever, cycles around the circle. If I make it slightly bigger, again, the same thing's going to happen. There's a sweet spot, right? And that's where the electron orbit lies, is right in the sweet spot, right where the right where the electron's wavelength constructively interferes. And this is, remember, due to h over p, which is the de Broglie thing. But if you imagine back from 4a, you have the waves on the string. So you have two fixed ends, and we were vibrating the waves onto the string and having them bounce back and forth so that the wave was standing on the string. It's basically like taking the two ends of that and just connecting them. Okay? The gaps between energy states occur because the next energy state up from this has to be the 5 state. And that means I have to be able to fit 5 lobes of a wavelength around it. Okay? And so that means I would have to have a situation, like I'm going to have to make this slightly bigger. I would have to have a situation more like this. And there's your 5 state. It's kind of gingerbread man, or plasmoidal ectoplasm. Whatever it is, it's one of these. So it goes from the 4 to the 5 state, but anything in between that, right? Anything between the size of that circle and the size of that circle means that you have a destructive interference happening with the matter wave. And that's why there's a gap in the energy states, because the electron exists only with this going on or with that going on, but nothing halfway between, because that means there's destructive interference. So this is a situation in which we're really using the idea of matter acting like waves to try and explain why the gap exists. The fact of the matter is that the gap exists, and it's a shift in thinking. Because for us, the shift is that there is no gap, right? The shift for us would be we don't experience non-continuous energies very often, right? In other words, if you hit a baseball, it doesn't leave the bat and then automatically say, oh, I can't be at that one, so I got to jump up to, I got to jump to this height, right, or something like that. It does if it's going into the stands, right? Some of the home runs go into the just over the fence. Some of them go into the second deck. Some of them go into the upper deck, right? Or something like that. Sure, then that's a situation where there's a discrete gap between, hey, the ball landed way up here versus the ball landed down in this one versus the ball landed down in this one, right? Sure, that's a situation where there's a gap between these energies of the final energy of the baseball, sure. Other than that, we're not really, other than in baseball, we don't really typically run into this. That's not even true, but just imagine you're driving a car and you have no ability to go between 30 and 35 miles an hour. You have to go from 29 to 37 or 36 or something, right? It has to somehow jump those speeds. You can't have an energy that's in that range, right? That's basically what this is telling us. There is no possibility that the electron can have an energy between these two. It doesn't exist. So, when it comes to drawing this type of thing out and imagining using some mental cues, some mental visualizations to kind of help us on the track of this, I usually come back to the staircase. So a staircase, kind of like the baseball upper deck tiers, right? A staircase is a situation in which we have discrete amounts of energy, say, between one and another. Okay, it's overdoing it to say there's no energy state between the two. There is, right? I can put my ball here, and it could be there. That's fine. So this is not a 100% great model. The idea is that it could be at rest here or here, but not in between. So a staircase is I like it a lot because it offers a lot of easy visualization. So let's do this. Something like that. Okay, so let's see here. I can't still quite see it there. Okay, so there's the first time I can get you to see the stairs. So here's staircase, right? Now normally I would build a much bigger one, but that doesn't seem to be useful in this case. The idea here, when thinking about energy levels in the we'll start with the hydrogen atom, but ultimately this is going to work to become more general than just in the hydrogen atom. We have energy levels. And so we make an energy level diagram, which is basically just a ladder with different spacing between the rungs. Going from the n equals 1 state to the n equal 2 state should be a pretty big jump, but then it should be nowhere as big going to the 3 state. Let's suppose that we're going to do the 3 state here, and then the 4 state, and then the 5 state, and then the 6 state. You know, they start to get kind of close together like this. And we can use this to determine the wavelength of the photon that's emitted when an electron drops between levels. So I want to use the staircase to just kind of imagine how that happens. We take the electron, and I don't know if you ever did this when you were a kid. My grandparents had a house that had a lot of stairs because they did not live in California. The house I grew up in had no stairs, well, other than the front porch stairs. That's it. But I grew up in a house basically with no stairs. So when I went to my grandparents' house, it was like, oh wow, stairs, cool, staircase. And this, we were easily amused back then. So you could take a ball, and there was a landing, and so the staircase went down, hit a landing, turned, and came down like this. So if you were really good, you could get a ball from the top, you could let it go, and if it went down right, it would hit the wall at the landing and then go down the next set of stairs. Pretty cool. So imagine that that's what you're doing with an atom. You're taking an electron from the ground state at the bottom of the staircase, and you're basically throwing it up to the top of the staircase and having it bounce down randomly and hitting different stairs as it bounces down. Now, again, it's not a 100% analogy. The electron does give off a photon for every bounce down that it makes, right? And it makes the photon based on the energy difference between the two levels between which it is transitioning. Okay? So for example, if it was a 6-to-2 transition, then this would be a very high energy photon. Not very high energy, okay? It would be largish in the grand scheme of visible ones. Like it would come down like this, right? And then it's going to give off a give off a photon like that. And this is the lambda 6-to-2. And we can calculate that based off what we've done before. So I'm just trying to give the idea of an energy level diagram and how it relates to a staircase. I really encourage you to use the staircase as a mental model for what is happening when you are thinking about electrons transitioning between states in a confined setting. Doesn't have to be only a hydrogen atom, but ultimately it works nicely because that gives off light and we can see it. So when you are exciting hydrogen gas, basically what you're doing is you're saying, okay, give me all your electrons, I'm going to throw these up with a lot of energy, and it's random amounts of energy, I'm just throwing them up to the near top of the stairs, and they're bouncing down, randomly hitting different stairs, giving off different photons. Some are visible, most of them are not. They get back down here, I scoop them all up, I throw them all up there again, they do it all again, right? So this is the ultimately what you might call a pumping of electrons from the lower ground states into higher energy states so that they can randomly fall between states on the way down. And you keep doing it and you get all these different wavelengths, like I said, some visible, some not. So we talked about how to do these calculations last time, I'm pretty sure, in the sense that we're using hc over lambda and for the energy of the photon, and then the 13.6 over the difference in the 13.6 times the difference in 1 over the energy levels squareds for the energy of the electron as it transitions between one to the next. So this is what an energy level diagram looks like. And you can certainly do other, right? You can certainly do other photons. The electron might transition like so. Okay, well, that's great. That's going to be a certain photon. We're not going to see that one. It's going to be in the ultraviolet. Remember, our visible range is really between about 1 and 3 electron volts. Okay? In hydrogen, this distance right here is about 10. So this is a little over 10 electron volts for hydrogen. Because remember, the ground state here is at minus 13.6. And if I calculate the next one, it's at minus 3.4. So right away, the difference is 10.2, and that's a UV photon. So anything that ends down here in the 1 state is part of what's called the Lyman. Yeah, I think this is called the Lyman series. Anything that ends in the 2 state we know is the Balmer series. Anything that ends in the 3 state, I think, is the Paxton series. And anything that's in the 4 state is the bracket. Oh boy. Am I getting these right? I may have flipped those around, but I think I got them. These may be here or here. I'm pretty solid on the first 2. I think that's the ordering. Anyways, this is the ending state, right? So anything that ends in the 1 state is part of what's called the Lyman series. And that came about much after the Balmer series because these are all ultraviolet and they didn't have the technology to detect ultraviolet photons at that point in time. So the same thing happened with these because these are infrareds, right? Here's the visible one. At least a small range of them is visible. And then you get to these ones which are much smaller in energy, and then these are infrareds, and these are in the far infrareds. So it gets smaller and smaller in energy. Okay. This idea of gaps between energy states, I mean, we could have a whole class on this, and I have had whole classes on things like this, like the entire semester on just talking about gaps. It is so fundamental to quantum mechanics, and it is so useful. We can now engineer materials with specified gap energies. Why is that important? Well, suffice it to say that basically you don't have one of these things unless we have gap energies that we can engineer. Right? That's basically that's how these things work, is because we can make materials whose conductivity and gap energies we control. If we couldn't do that, then these things just are not a thing for us. So with that being said, let's talk a little bit about what this does for devices. For example, let's talk about a laser such that its usage of the gap is primarily the way it works, right? So classically, we don't have lasers because because we didn't know about atoms and because of a lot of reasons. Okay, anyways, none of them really matter why, but let's talk about what lasers are and what they do. The light lasers emit is different. We know this. Okay, it's very thin. The beam is very collimated. It's of very high intensity. It is monochromatic, which means it's single wavelength. And the waves that it emits, or the photons that it emits, are coherent, right? So there are a couple of check marks that we would put down here. So we would say, what kind of light? So laser light, we'd say, is monochromatic. In other words, single wavelength, or at least approximately single wavelength. I should say approximately. Nothing's ever exactly a single wavelength. There's always a small range, and there always will be. But it's pretty darn good. It's collimated, meaning it's thin and it's a beam. What was another one I said? It's intense, and that kind of comes down to the collimation, right? If you've made something down into a really thin, small spot, well then you're depositing all that energy onto that spot. That's going to make it intense. And then the last thing I put was that it is coherent. In other words, that their phases are locked. That means that they are all swimming exactly at the same peak and trough. They're not coming out all willy crazy nilly like this. That's what you're getting out of regular lamps, is a phase incoherent amount of light. But from a laser, it's different. They all come out and they're swimming exactly in phase perfectly, and it's really cool. So let's talk about how they work. I want to talk about the workings of the helium neon laser, because ultimately it was the first one that was of such a build that it was useful for a number of things, and it worked on this principle of using the gas. So helium and neon are the two elements that we put together inside the laser, and they're gases. Now, most lasers you're going to see these days are going to be solid state lasers, right? So this is not 100% applying. All of this still does, because it's still true for the laser light, but the actual workings of it is slightly different, because it's a technological advancement to go from gas into solid state to make a laser. So helium neon, what do we do? Well, what we do is we excite the helium atoms. Okay, so helium atoms are pretty close to hydrogen atoms, and hydrogen atoms are relatively well described by the Bohr model. Helium is kind of also just kind of okayishly described by the Bohr model. It's not great, but it'll work in a pinch. You can fix it. So we're going to excite a bunch of helium atoms. Let's say they have a couple of states that look like this. So this is the helium. Here's the helium energy state ladder. And here is the neon state ladder, energy state ladder. Neons, we'll just put the ground states about the same. That. So that these two here actually are pretty close in energy. Okay? So what we're going to do is we're going to excite the helium atoms such that we're bumping the electrons up into, say, this state. Okay? How do we do that? By plugging it in. You basically provide an electrical shock, which is akin to, like I was saying before, imagining that you have at the bottom of the staircase a whole bunch of ball bearings, and you're just going to scoop them up and throw them, right? Some of them will go way up there, some of them are only going to go right to there, but you're going to scoop up, and that's what you're going to do. You're going to excite these things. So you're going to put energy in such that you pop the electron up like that, and it goes into this state. Now, what we can do is, when we have these things here, what's cool about this is, because this state is so close, if we take the energy that this helium atom now has and we bump it into a neon atom, what we can do is essentially have this thing, when it bumps, it decays, but it gives off that photon that goes all the way down to here. That photon could get absorbed by the neon electron, which will pop it all the way up here. Alright? So if it decays down and gives off photon, which then gets absorbed by this one, it puts the neon in that excited state. Why are we going through all this rigmarole? Because there's one thing that, there's a couple of things. There's one thing that a laser definitely needs in order to be active. In order to get an intense amount of light and also to get them to be coherent, we need to have a whole bunch of neons with electrons in this upper state. It turns out that in the upper state in neon, it's metastable. In other words, the electron can exist up there for a couple of extra, beats, if you like, a couple extra seconds, not really, before it decays down, right? So it's metastable. It's not going to exist up there forever. It's not the ground state. It's eventually going to be like, I'd really like to get out of here. But it will tolerate being there for a while. You can hold it here. Okay? What you need in a laser is to get more neon atoms with electrons in the upper state than you have in the ground state. That's called a population inversion. And the reason the population inversion happens is because this state has a longer lifetime than normal. If that didn't happen, then we wouldn't be able to get the population inversion, and therefore the lasing action would not work. Okay? So, why do we need multiple atoms in a state like this? Okay, so here's what we do. What we do is we get a whole bunch of atoms like this. Many neon atoms with their electrons in an excited state here. Okay, so we have many neon atoms in the excited state. That's known as the population inversion. Once we have the population inversion, then what we're going to do is we're going to allow one of them to decay. Well, it's not like, check in with me first. No, it's going to happen no matter what we think. Okay? At some point, one of them is going to say, look, I'm tired of being up here. I'm going to decay. It's going to drop down. It's going to drop down through this right here, and it's going to give off a photon here. This happens to be a red photon, a visible photon, which is then going to go to another neon, which is over here, which also has an electron in the upper state up here. And when this photon reaches over here, it's going to just kind of shoulder itself into this electron and cause that electron to decay also. Right? So as this thing comes this way, what happens then is this decays, and now, whereby I had only one photon before, I now have two, and they're identical. It's this process that we need the population inversion for. Okay, it's that process, because what happens is we then end up with a large cascade of this energy photon coming out, and they're all causing this exact transition, which means they are creating more of themselves. This is basically a chain reaction. It happens so quickly that the neon atoms decay, and then the electron falls back down to its ground state, by which time it gets hit by another helium atom again. Because we have so many of these, right, that we continually then use them to re-excite the neons. And then it's this transition in the neon that actually produces the laser light, right? That's the laser light right there. So when the neon's up in here and it gets bumped by one of these photons, its electron decays to that state and emits that exact same photon. All right? And in doing so, it happens that the photon is exactly in the same initial phase as the one that bumped it. So the light that comes out is, in fact, phase locked with the light that created it. And that is part of how the laser works. Okay. Now, your job now is to make sure that you keep putting in enough energy into all these heliums that they can transfer their energy to the neons and keep the neons such that as soon as this one decays down, it's getting pumped back up right away. Right? As soon as it leaves, that photon leaves and this thing drops, we're putting the energy back in. And that photon causes this one to drop, we're putting the energy right back in. Right? All we got to do now is put a mirror here and a mirror here so that the light just keeps reflecting back and forth and building up more and more and more photons because they keep causing the neons to decay. And so that's what this process of the naming became. Do you know what the word laser actually means? Well, light, yes. Well, it's what it means is it's light amplified by stimulated emission of radiation. And that's what this process is. It's stimulated emission. In other words, I have this neon. It's all set to decay. The electron's in the upper state. It's metastable, so it's not going to go immediately. But it will if it's prompted by the exact photon that it would emit if it decayed between here and here. So the photon coming from this one stimulates the emission of another exact photon when that one comes by and bumps this electron, and the electron goes, oh, I could make one of those, and it drops. There you go. This process is known as stimulated emission, right? So now all we got to do is, I got these two photons coming back this way. These neons have decayed. I'm going to pump them back up with the heliums, right? With all the energy that the heliums carry, I'm going to put the neons back up. These two photons are going to come back. They're going to hit these two things. I'm going to get two more photons coming out. They're going to decay. I'm going to pump them back up. Now we've got four photons, right? And I'm going to just bounce them back and forth until they get to become a really not solid, but intense beam of light. Notice that they're all going through the exact same transition. Therefore, the photon is of the same wavelength every time. So that's why the monochromatic comes out here. They are swimming in phase because of how the transition of the electron is caused by the stimulated emission. So that's taking care of the coherence. And ultimately, all I need to do now is, instead of having this be a perfect mirror, make this a 99% reflecting mirror, and now some of it comes out. Like 1 out of every 100 photons comes out, and that's what we call the laser light. So that's basically how a laser works. Note, it depends on a couple of things. I mentioned the gap. It does depend on the gap because, right, this is the transition between which we want the electron to go such that it emits that particular energy photon, right? It's not any energy, it's that one. So the good thing about that is that between this state in the helium and this state in the neon, there's a very, very, very small gap. And usually that is going to be made up for by extra kinetic energy of these things relative to one another. So if this decays and lets a photon out, and it kind of bumps into it or something like that, causes it to jump, gives it a little bit of extra energy, that causes the electron to jump all the way up to here. Instead of just stopping here, it makes it up to there. That's what you need. Okay, so we need to be able to get the energy of the electron in the neon to be all the way up there, and we need that to happen for most all of the neon atoms. As much as possible, we need the neon atoms to be in a state of carrying the electron in an excited state. Okay, that's what the goal of the laser is. Keep the neons in the excited state such that they cause themselves to continually decay and emit this particular light.
right? So if you're thinking about a staircase, it's that you make the exact same transition between the same two stairs every single time. Right? You always go from this one to this one, and that's the light that comes out. Okay, so that's essentially how lasers work. It's like I said, it's very simple, and it's I am glossing over a bunch of details here, but ultimately, in a fun way of thinking, Einstein was one of the people who put a lot behind the prediction that this could happen, like what would be going on. He was actually the one calculating a bunch of the quantum amplitudes in order to see if this would work. And it turned out it did, of course, because that's why he's Einstein. But anyways, the idea being that the helium atoms are just carrying the energy to the neons, and the neons are the ones that are actually making the transition of the electrons between the two levels, such that they emit light that stimulates emission from other excited neon atoms. Alrighty, so we're here, I think with this, I want to talk a little bit about the more modern formulation of electrons, or I should say quantum particles, in trapped situations. Okay, so we generally call these, when you trap something, we call it a well. And I want to introduce the idea of the Schrodinger approach to doing this. So I want to maybe motivate a little bit about the Schrodinger equation so we can talk about it. We certainly don't have very much time to go through and do a large amount of solving of things like this, which is fair because ultimately that's not really one of the points that we would have here. That would be more left to a course that's more geared towards solely quantum mechanics. But I want to at least give you a rundown as to how it came about and what it does for us, okay? So the Schrodinger equation is basically another attempt at conservation of energy. If I take it in its simplest form, in other words, I'm going to take a one-dimensional problem, and I'm going to remove any time dependence from it, okay? So that I'm going to get only these kind of standing wave solutions that kind of like I talked about with the Bohr radius here. The Schrodinger equation is basically energy conservation in the sense that we just write down how we calculate the energies in a slightly different way, but ultimately we're doing it with the particles, what we know about the particle, and we're applying it to what we know about the particles. So we're basically kind of constraining it. We're writing energy conservation. We're basically going to write kinetic energy plus potential energy equals total energy. That's all we're going to do. Now, it's going to appear pretty strange looking because we're trying to apply these energies to a quantum mechanical particle, and we're going to use this to try and solve something about the particle. So what we say is that the particle has a wave tendency to it, okay? It has a characteristic to it that causes us not to know stuff about it. In other words, like I was telling you with the double slit experiment the other day, the electrons go through the slits, but they go through both slits at once, right? They don't interfere with a neighbor, they interfere with themselves. So there's something that's wavy-ishness, and I mean that with as much technical savvy as I can muster. There's some kind of wavy-ishness about the things
that is not manifesting itself when we look at how we ejected an electron from an atom, right? It came out as a particle, and when it hits the wall, it hits as a particle. So there's something fundamental about how the electron goes from one place to another that we are missing. This is where our wavishness behavior starts to poke its head, right? Okay, so we're going to say, all right, there's an issue that we have here, and that is that if I shoot an electron through the double slit experiment, I can't tell you where it's going to end up. As much as I think that should be possible, in the sense that, like, I'm shooting a baseball and it's going to go hit over there, or it's going to be caught by this person or whatever, I can tell. But if I shoot an electron through a double slit experiment, there is no trajectory, right? There's no path it follows. It's wavy-ish. And so we lose the ability to be Newtonian about the whole thing, right? And say, oh, there's a definite path that goes from here to here, it's going to land right there. We can't tell you that. If I emit it here, it might end up down there, right? I don't know. What we can do is give you probabilities about where it's going to end up. So there's things about the particles that are contained in this kind of wavishness that make it such that we can only predict probabilities of where something might end up. Okay? That thing is called the wave function. The thing that we use to represent this idea of wavishness probability stuff about a quantum mechanical particle is called its wave function. Okay? And the wave function embodies essentially everything that we can find out about the particle. Alright, I'm gonna say it's the tool we use to try and know stuff about what's happening. So ultimately, we know stuff about, say, an electron because we know something about its wave function. How does that help us? Well, the wave function, ultimately, if we square it, it gives us some insight into what is a probable outcome. So the wave function might tell us that there's a large amplitude here, which means there's a high probability of something happening, but there's zero amplitude here, which means, you know, for example, in the double slit, I'm not going to see electrons landing there. I will see them landing here or here, but not right here, right? Like there's a gap between the two fringes. Yeah, there is. And so the wave function is the tool mathematically that we use in order to keep track of the information that we have, and then ultimately to try and make predictions, okay? The wave function itself is not physical in the sense that you don't build a wave function detector. What you do is you build a probability situation. In other words, you build a couple of setups of the same thing, and then you get this, the initial conditions all exactly the same, and then you start the experiments all simultaneously such that you know, half of them are going to come out this way and a quarter of them are going to come out that way, all right? And that's the information the wave function contains. You have to manipulate it a little bit in order to find out how to get probabilities and things like that. But ultimately, that's what the wave function contains. All right, so when we write the wave when we write the Schrodinger equation down in terms of the wave function, it basically is this applied to one of these. And so if you've had Math 6, this might look familiar. This is an eigenvalue problem, and we consider the wave function to be an eigenfunction. The total energy is going to end up being an eigenvalue. And if you don't know what I'm talking about and none of those words make sense, it doesn't matter. Don't worry about it. Unless you want to, and then you can go find out about it. It's pretty cool. So the kinetic energy operator of the Schrodinger equation looks essentially like momentum squared over 2m. With two derivatives with respect to position. That is what we call the kinetic energy operator. And then we're going to operate on the wave function, and the wave function is going to be this thing right here, which maybe we'll call psi of x. It's a one-dimensional. I'm only doing this in one dimension, so that's the wave function. That's the thing we use to keep track of information about the particle. Right? So then we're going to add to it the potential energy of the situation, which is going to be like V, or actually I'm going to call it U of x times psi of x. Okay? So that's the kinetic energy plus the potential energy, and that's going to equal the total energy. The total energy is just E times psi of x. Incidentally, the wave function is represented by the Greek letter psi, which basically means it looks like a pitchfork, kind of held upside down, or Poseidon's trident. I think that's where Poseidon got the name, because psi. I don't know, maybe that's true, maybe that's not, I actually don't know. I'm going to go with yes. So anyway, the Schrodinger equation looks basically like conservation of energy, all right? It looks crazy and weird, but don't worry about it, it's fine. Let's do a quick solution of this and see if we can find some allowed energy states. And when we're doing this, I'll show you some of the highlights of how to use the Schrodinger equation and what to interpret when you are looking at it. Because ultimately, we're not going to do a lot of solving, but I do want to see if we can do some interpretation. Okay. Let's start with the easiest possible potential energy, which is 0, within a certain range. Okay, so let's suppose that it's 0 within this range, but it's infinity outside it, which means that I have definitely trapped the particle in this range here. And it's not outside it because the potential energy is just too big out there and it can't make it. Right? So let's imagine that I have a potential energy that looks like this. 0 between here and here, but goes off to infinity for the rest of whatever. Right? In other words, it's infinity out here, out to infinity, and it's infinity out here, out to infinity. But right in here, between, say, x equal to 0 and x equal to L, right, the length of the trap, I have a 0 potential. If you're a quantum particle, you tell me where you want to be. Right? Is it going to be amongst the rocky battalions way up top here where you have to struggle to live and work, or is it down here where you're on the couch, probably eating potato chips? Okay. I'm going no further with that one. So yeah, it's going to be down in here. So what we're going to do is we're going to try solving for the wave function of the particle within this region. Okay. What do? Well, what we're going to do is I'm going to take this thing here, just take this first coefficient, just multiply it over, because the potential energy is 0 at this point, so it's really just this thing equals that thing. And what it ends up looking like is two derivatives of the wave function equaling a negative constant times the wave function again. In other words, two derivatives of the wave function equaling negative some constant times the wave function again. This should be very familiar, right? There are many times we run into differential equations that look kind of like this. And hopefully you've seen or are aware that the solution to this is basically a linear combination of sines and cosines, or if you like, complex exponentials. But we'll just stick with the sines and cosines. All right, this means that the solution
is going to be some type of A times sine kx plus B times cosine kx, where k is the square root of this coefficient right in here. Okay? The square root of that thing. This looks hopefully very much like a simple harmonic oscillator problem out of 4A, where you'd say, instead of x, you'd have had a time here. This would have been x, so you would have like an acceleration term over here, and then you would have had x over here, and then you would have some omega squared here, and that negative sign out front, and you would have said, oh yeah, it looks like a cosine or a sine or a something. So the point being that k is the square root of 2me over h bar squared. All right. Now, what we need to do is understand that I've got this oscillating wave function, right? It's not oscillating in time. There's no time to this. It's frozen in time. It's a standing wave, but it is oscillating in space. All right, so it does have differences in its spatial distribution, but not in its time distribution. Right? So what we need to realize is that I need to match the wave function, because what I'm really doing is I'm using this to keep track of the particle information, but if I throw stuff away, then I'm voluntarily throwing away information about the particle. Look quickly at these two regions outside the trap. Out here and out here, the potential is infinity, and it's going off to infinity. Okay. Now, as much as you might say, come on, that's not realistic. True, but remember, we only build models that are simple. You can actually make stuff like this and trap an electron such that it acts quite like one of these, right? So what we're doing is a simplification of it in order to not have to worry about pesky mathematics. But ultimately, you can make these, and they do work as the solution tells us it does. I mean, otherwise, what are we even doing here? So what we have here is the wave function of the particle out here must be 0, because the particle should have no possibility of being found where the potential energy is infinity. It can't be there. It would need infinite energy to be there. And I'm pretty sure a particle can't have infinite energy. So, this, if we ignore, it's throwing away information. We don't want to do that. What we do want to do is say, I want to link up what I'm going to find in here with what's going on either side of it. That means I need the wave function to be 0 at both of these points right here. Okay? You can probably see pretty quickly that that eliminates the cosine component to this pretty quickly. That means this thing has to be 0. I can't draw a cosine which has a 0 on both ends. If I draw a cosine that has a 0 on both ends, I'm basically drawing a sine which has been phase shifted. Or I'm drawing a cosine that's been phase shifted so that it's a sine. That's what I should say. All right, but I've already included the sine component as part of the solution, so okay, let's just look at the first possibility. What's the first thing that I can do that is 0 here and 0 here, and looks like a sine? Wouldn't it be that? There you go. That's the one state, right? That's your ground state. That's what the ground state that's what the ground state particle distribution is going to look like. All right. So if I went to the second state, I'd need to think about the state in which I could still use a sine but end up at 0, having started at 0, and I think you can see that that would be the one which looks like that. Right? And these are exactly, if you remember I was talking about this earlier, these are exactly the same as the set of allowed wavelengths on a fixed end, a string with 2 fixed ends, which we're driving with a wave driver,
right? And we bouncing this thing back up and down. If we
You're forcing the wave to be zero at the two ends, which is what we're doing here in this example, then the allowed set of patterns are only sine wave components, bits of a sine wave or bits of more sine waves or anything like that, because sine's the only one that's going to start and end at zero, right? So it's that set of wave functions that we find here describing this particle in a one-dimensional trap, where I've caused it to be only within here and it can't be outside, all right? So I want to use this idea as our starting point for visualizing wave functions. And I want to spend a little bit of time talking about how to visualize wave functions. Now, notice, this is a spatial distribution of the particle. In other words, if I drop the particle in here, it's going to assume this type of spatial distribution. And I'm going to try measuring where it is. And most of the time, like if I set up 100 equal traps and I go, okay, measure the position. Most of probable, I will find the particle at the halfway point. That's the most probable situation. Because remember, the wave function gives us information about the particle's whereabouts. It's most likely to be right there. That's where it's highest. Notice though, if I'm in the first excited state, it should never be in the middle. This wave function here crosses through the middle, which means that it should have a zero probability of being found right there. It should have a pretty high probability of at the 1/3 slot here and at the 2/3 slot here, but not at the 1/2 slot. I should not find the particle there. And this tends to make people say, huh, and be confused as to why that is. And that's a fair thing to be confused and asking why that is, because essentially what you're doing is you're excluding the particle from existing at a particular point in space for no other good reason other than wave interference. Well, I guess that's a pretty good reason. It's going to have to be, isn't it? Because that's all we've really got. So yeah, the particle won't exist at the very mid spot when it's in the first excited state. Okay. So we get to this idea that the wave function, at least in this case of having a trap, is kind of a I don't want to say it's oscillating, because that makes you think it's waving up and down. It's not. It's like a standing wave. It's stationary in time. It changes with space, and then it's zero out here and it's zero out there. Now, I think when we come back tomorrow, I will talk more about what to look for when we start making modifications to this type of trap, and what does that mean from a wave function perspective, so that when you can look at wave functions, you can be a little bit more comfortable looking and seeing, oh, when I see one of these in a wave function, it means that this is happening. All right, so we'll go from there. And I think I'll leave it at that today, and we will have only one more class meeting, which will be happening tomorrow. So with that being said, have a great rest of your day, and I will see you then.